In this presentation, we're going to be looking at using the chi-square test to see whether the outcomes of some breeding experiments follow Mendel's law of independent assortment. Now, the first thing you need to do when you're doing a chi-square test is to work out a contingency table. So we're going to look back at the example we saw in the first lesson on linked genes with the purple and red flowers and the long and short-shaped pollen. Now, if you remember, when they got the results for the breeding experiments between two heterozygous, two F1 plants, they found that they could see straight away that they didn't follow the expected ratios of 9, 3, 3, 1. But when we're doing chi-square, just to prove this is the case, we need to work out what those expected numbers would be. So first of all, you need to know the total, which is 2, 1, 3, 2. And then you need to divide that by the total number of possible outcomes. So you add 9 plus 3 plus 3 plus 1 together and you get 16. So you do 2, 1, 3, 2 divided by 16, and that equals 133.25. This has been rounded up a little bit. So then you put that into the expected number. So 1 times that is obviously 133.25, and then 3 times is 399.25, and 3 here, and then you times it by 9 to get 1199.25. So now we've got our observed numbers, and we've also got the ones we would expect if they followed the 9-3-3-1 ratio that follows Mendel's law of independent assortment. Okay, so now we need to look at the chi-square equation. So this is the chi-square test, and this is the equation, and you can see that we need to do chi-squared here, and this is the sum of all the observed minus the expected squared all over the expected. Now, just looking at this equation, you can see that the bigger the difference between O and E, the bigger the value we're going to get for chi-squared. So the bigger the value you get for chi-squared, the more likely it is that there's a bigger difference between what we observed and what we expected. So therefore, it's not following the pattern we expect. But what we also need to know is, how significant is this number? So that's what we're going to be looking at. Okay, so let's look at this. So this is the table. So I've put the observed results here and the expected here. And then you just work out this O minus E squared, and O minus E squared divided by E. And then you'll get a total in this box here, and that's going to be your chi-squared value. Okay, so let's have a look at it here. I've already done all of this. I've done all those values and put them all in, and we've ended up with this value for chi-squared. Now we can already see that's quite a big number. And we know this because we could see very clearly that these values in the observed column did not fit the 9-3-3-1 ratio. There was quite a lot of difference. But just to prove this, we need to use a probability table. And before we can use a probability table, we need to know two things. We need to know what the degrees of freedom are. And in this case, the degrees of freedom are basically the number of categories. And we've got 4 different categories for red with long, red with short, purple with long, purple with short. And it's the degrees of freedom is n minus 1. Okay, so we also need to know what our critical value is. So on this probability table, we're going to look at the probability of 0.05. This means we're 95% confident that if the critical value is higher, if the number for chi is higher than this critical value, then we can be 95% sure that there's definitely a difference between what we observed and what we expected. Okay, so let's have a look at the probability table. So we've got 3 degrees of freedom because it's n minus 1. And this is our p equals 0.05. And so our critical value is 7.82. So that's our critical value. And our null hypothesis is that there is no significant difference between the observed and the expected results. Now, our value of 9 0.65 is obviously much, much greater than 7.82. So we actually reject the null hypothesis. And we know from looking at this that these two genes do not follow Mendel's law of independent assortment. There is definitely a big difference between what we observed and what we would expect if they followed normal ratios. Therefore, we can conclude that they do not follow Mendel's law of independent assortment, and that's because they're linked on the same chromosome. Okay, so now you can try this question. In vampire bats, round ears are dominant to wrinkled ears, and pointed noses are dominant to flat noses. So a pure breeding round-eared and pointed-nosed bat was crossed with a wrinkled-eared and flat-nosed bat. So we've got our homozygous dominant, and we make that with the homozygous recessive. So, and then we produce the offspring, the F1 generation. Two of these offspring from the F1 generation were bred together to produce the F2 generation. And the outcome of the mating is observed in the next slide. So you need to use the chi-squared test to determine whether this pattern of inheritance follows Mendel's law of independent assortment. And here is the table showing the observed results for this breeding.